So today we are going to discuss the colors that you see in transition metal complexes. Basically, that arises due to absorption of light, absorption of visible light. If anything, any material, any compound absorbs visible light, a portion of visible light is absorbed, it will definitely have color. Okay, so it is the absorption of light that gives rise to color. And in the case of metal complexes, now that we have gone through the bonding theories, valence bond theory couldn't explain the colors. CFT, yes, it was able to explain, and that still forms the premises on which we are still explaining the colors. And the same element of CFT is carried forward in case of ligand field theory, where molecular orbital theory was implemented, realizing that these ligands are not just point charges, they also have orbitals, and they can overlap, can happen. So the basic idea for the colors in the complexes that we could see was that, so the variety of colors that we see is due to basically the splitting of due to the ligand field. Okay, so suppose you have one electron in the ground state of, so this is your uh, T2G and this is EG. So if it is vacant, if you provide enough energy, suppose, then this transition can happen. So if you are providing in terms of wavelength, suppose 611 nanometer light, so this particular thing can happen. So typically this in titanium and some others, so look at this spectrum. Yeah. So this is the absorption spectrum. Now you are familiar with this. You have first-hand experience of taking this absorption spectra of complexes. You have already prepared nitro, nitrito, amine complex, as well as iron thiocyanate complex, and taken the spectrum. I hope all of you have taken the spectrum. So absorbance versus, so this is the thing that you see, wavelength. Okay. And so for example, in this case, chromium, it is all the complexes of chromium that has been shown. Chromium H2O6, water as ligand, fluoride as ligand, cyanide as ligand. 380 nanometers, so it absorbs in the UV side. Ultraviolet region, very high energy is required for this transition. This one absorbs at 570 nanometers, one absorbs 650 nanometers. So they will have, what do you expect in terms of colors? Something that is absorbing in the UV region, it will not have color, it will appear almost white, sometimes off-white, because of the tail that it has in the visible, the tail is in the visible region, so some color will be there. It will look like off-whites kind of thing. Okay, but you can see these things. So this is the color that has been absorbed. So this is the color absorbed here. So the color that is absorbed doesn't reach your eye. The other portion that has not been absorbed will be scattered, or that it will be transmitted. So depends on the observer. आप एक टेस्ट ट्यूब को आर पार देख रहे हैं, तो ट्रांसमिटेड लाइट में जो ट्रांसमिट होके आएगा वो आपकी आंखों तक पहुंचेगा. कुछ एब्जॉर्ब हो गया, वाइट लाइट इधर से आ रही है विंडो से, और बीच में टेस्ट ट्यूब रखा है, आप इधर से देख रहे हैं. तो ऐसे केस में क्या होगा कि वाइट लाइट उधर से आ रही है, something is at is reaches the test tube, you have sample placed there, it is absorbed, and then transmitted light gives you the color. So if you want to correlate this, so transmitted light, some of the components are missing, of white light are missing, and the component that reach your eyes, that gives the perception of color. तो ये हमेशा याद रखिए, जो आपकी आंखों तक पहुंचेगा वही कलर का परसेप्शन देगा, जो एब्जॉर्ब हो गया वो कलर का आभास नहीं देता है. ठीक है. Okay, so that's so this is how we correlate this. Something that was 380 nanometer very high energy, so splitting is more. See this picture, 570 nanometers, something it is less, red violet in color, yellowish color. I told you because of the tail. Actually, the peak lies in the 380 nanometers, which is ultraviolet region. But because a small portion is in the visible region, the tail of the absorption spectrum, so a little bit of color, very faint color, yellowish in color, you'll observe. But in this case, it will appear when yellow color is absorbed. The other things that dominates and the other component reaches your eye, and the dominant is in them is the red violet. When the red something 650 nanometer is absorbed, this is red, so that is the red part of the spectrum. This is your Vibgyor. Do you realize this, what I am showing here? This is your what you know as Vibgyor, right? And the portion that is absorbed is not reaches your eye, does not reach your eye, and has nothing to do with the perception of color. Only the portion that is not absorbed somehow reaches your eye, either through scattering, through transmission of light. So it will be, so something which absorbs red appears green, something which absorbs the yellow color, that appears red or violet, purple colors things. So this is the complementary that we have, colors in complexes, which arise mainly due to the splitting of d orbitals. So because the energy gap matches with a particular wavelength of light, visible light, and then you, if uh, if you make that white light incident upon it, you will see those colors. So it is basically the crystal field theory that explained initially all these colors in case. And there are certain other considerations that will come into picture. So it is basically the electronic transition that we are looking at, and whenever there is electronic transition happening like this, if the energy of the that transition required is falls in the visible region, then color will be there. So sometimes you do not see any colors that may happen due to electronic transition when it is the electronic configuration is something like this, outer shell with 18 electrons or some like this. So basically the origin of color, what we have seen so far, if yellow light is absorbed, white light is falling on the sample, the yellow component is absorbed, and so the transmitted one, if the observer is on this side of this, the transmitted light, you will get the blue one. Appearance is blue light is transmitted and makes the appearance. And similarly, if you have in the second case, copper tetrachlorocopper, so Cl4Cu. So blue, in this case, the blue component of the visible uh, white light is absorbed, and so the remaining one has a dominance of yellow, and so that reaches the eye and appears yellow to you. So this is the idea. The same thing, see, this was in the transmit when the observer is on this side of the beaker or test tube and the solution is kept here. If it is opaque, like something you are putting on a surface, powder on copper powder, copper sulfate on the surface, it will appear blue. So in that case, you are looking at the scattered light. The scattered light reaches your eye, and that has one of the components of the white light is missing. Some of the components are missing, and others which reaches the eye gives you the perception of color. So these are the things how the colors are observed, the absorption of light and the observed color. So these are the things that we see: absorbing species, absorbed color, and the observation, the color that appears to you in the transmitted light. So the ligands, if you keep the metal ion fixed, cobalt here, okay, in all these compounds, but the this variation of this ligand can bring about the changes in colors, and that is due to the crystal field splitting, ligand field splitting that we had discussed earlier in bonding. Now, so very at a very fundamental, what do you see here? Electronic transitions, just it is not a phenomena that is happening in metal complexes. ये आपने देखा कि जब हाइड्रोजन एटम है उसमें भी इलेक्ट्रॉनिक ट्रांजिशन होता है. We have talked about electronic transitions, electronic spectra for hydrogen in a simple atom also. So what is a very fundamental thing that happens? It is, so electron moves from one orbital to the other, and the energy is matched by the incident light. So incident light falls, there is a incoming, there is a source of light which uh, source of light, the light is made incident upon the sample, वो लाइट पड़ रही है सैंपल पे, और एब्जॉर्प्शन होता है जब ये जो एनर्जी की रिक्वायरमेंट है ग्राउंड स्टेट से एक्साइटेड स्टेट के लिए वो मैच कर देते हैं आप. सो दैट एच म्यू, द एनर्जी ऑफ द light, is matched with the this quantized energy levels. So that kind of, so that you see, one thing very important here, the things that so at very basic level, what I am saying, trying to understand, because if you do not, I had initially told you before bonding that to understand bonding you need to understand the atoms, you need to understand the electrons first. And throughout, when I started valence bond theory or molecular orbital theory, I told you that the modern understanding of electron is that we treat electron as a standing wave. After the de Broglie's and other things, Heisenberg's principle, there was view that the failure of Bohr's theory and other things clearly indicated that that particle nature of electron is not able to explain most of the things. Most of the things were not explained by particle nature of electron, and we have to visualize them as wave, and not just wave. Standing wave is important when we are talking about electrons within an atom. They behave as standing wave. That is clearly you can see when you tie a string at two ends and then pluck that string, you get one loop or two loop. So that is a standing wave. So you have to visualize it in that kind. And that standing wave, so it is like one loop or two loop. So you are gradually increasing in energy in this. So little bit, so this is the energy. So मतलब आप ऐसा समझिए कि आपके पास ये स्टैंडिंग वेव है और आपने उसको एक फॉर्म से, एक वेव फॉर्म से दूसरे वेव फॉर्म में चेंज किया. वन लूप वाला टू लूप में चेंज हो गया. ऐसा आपने कुछ एनर्जी दी है और वो टू लूप वाला बन गया, फिर टू से थ्री वाला बन गया. सो यू आर ग्रेजुअली गिविंग energy to the system, energy, then two loop, you give more energy, it will become three loop. So it is so this is like, so this is what we mean by transition. When we say electron is going from 1s to n is equal to 1 to n is equal to 2 orbital, so the energy level, that means the electron, which is a standing wave, is changing its profile. The wave profile changes. Okay, There is no box, there is no vessel, there is no container in it. Electron goes and sits. The orbital is not a container, nothing like that. Or a one electron wave function is an orbital. That's what I told you. Simple. And that wave function is a representation of a standing wave, three-dimensional standing wave. And only a part of that you were constructing. The जो आप गोल गोल ऑर्बिटल बना रहे थे एस के लिए, वो एंगुलर पार्ट ऑफ द वेव फंक्शन था. So it is the so this is this kind of thing that is happening. ठीक है, मतलब एक स्टैंडिंग वेव को दूसरे स्टैंडिंग वेव में ट्रांसफॉर्म करना है. यही यही इलेक्ट्रॉनिक. सो इलेक्ट्रॉन भी एक स्टैंडिंग वेव है, उसको आप एनर्जी दे रहे हैं, वो एक फॉर्म से दूसरे फॉर्म में ट्रांसफॉर्म हो रहा है. लाइक द हियर वी सी वन लूप से टू लूप में जाना, एक स्ट्रिंग का टू लूप से थ्री लूप वाले स्टैंडिंग वेव फॉर्मेशन होना. सो इस तरह से जो हम विजुअलाइज करते हैं, यही this is the visualization that you need to develop. Okay, so this is what happens. And so this was the thing that initially I had told you that okay. So now when we are talking about uh, so what I have just told you, अब इसको कैसे visualize किया जाए, right? So think of hydrogen atom, and suppose we are talking about transitions, electronic transition. So n is equal to 1 first energy level to n is equal to 2 in hydrogen atom. So something like this. Then what should have happened? क्या होना चाहिए था, कैसे, क्यों हो रहा है और कैसे हो रहा है, इसको समझने की कोशिश कीजिए. So this is the profile. There are two things that can happen. You have one is, and so this was initial spherical wave which is transforming in 2s. So this is a transformation of one wave profile into another one. And the second picture that we have is initially it is 1s transforming into a 2p. I told you a 2p orbital is drawn as a two tangent spheres, right? Dumbbell is the square of that wave function that gives you dumbbell-like shape. That is electron density. But wave profile is two tangent spheres, yellow colors that you see. And then, yeah, I told you. So you can see here what is changing here. So, you know, when I tell you that in hydrogen atom, I am giving energy in form of h mu, the visible light is falling upon it. So what should be the transformation? Whether 1s electron should go from 1s to 2s or 1s to 2p? What should have happened? Any idea? सिंपल सा क्वेश्चन है. अगर इलेक्ट्रॉन 1s ग्राउंड स्टेट में है, हाइड्रोजन ग्राउंड स्टेट, राइट, एंड दिस इज द फर्स्ट एक्साइटेड स्टेट. उसमें कई सारे ऑर्बिटल्स हैं. किस ऑर्बिटल में जाएगा? 1s में जाएगा, सॉरी 1s से 2s में जाएगा या 1s से 2p में जाएगा? हेलो, ओके, या दोनों में जा सकता है? हेलो, 2s में नहीं जाएगा? 1s? बस अब यही चीज रटने से मुझे प्रॉब्लम है. आपने, हाँ, सब आंसर सही है लेकिन आपने समझा नहीं है. अब मैं आपको बता रहा हूँ कि हाँ ठीक है, द आंसर इज करेक्ट. इट विल गो टू 2p, नॉट 1s टू 2s नहीं. अभी आप वो भूल जाइए कि डेल्टा एल वाला जो रटा हुआ है उसको भूल जाइए कि डेल्टा एल कैसे, वो कैसे आता है, उस पर हम पहुंच जाएंगे अपने आप. अब अब आपको यही यही बताने के लिए, क्योंकि वो अगर आप समझ गए हैं तब आप कॉम्प्लेक्सेस में भी अप्लाई कर लेंगे. ठीक है, प्रॉब्लम यहीं पे है. हाँ, तो 1s से 2s में देखिए. So now what I am saying that it is 1s इलेक्ट्रॉन इज अ वेव, लाइक ठीक है, स्फेरिकल वेव प्रोफाइल है, छोटा सा स्फीयर अंदर दिख रहा था, ब्लू वाला स्फीयर, बाहर वाला भी है, स्फेरिकल वेव प्रोफाइल है 2s। तो ओवरऑल सिमिट्री में कोई चेंज नहीं है। द इलेक्ट्रॉन डिस्ट्रीब्यूशन डजंट अंडरगो एनी चेंज व्हेन a 1s wave, electron wave, which three-dimensional electron wave transforms into a 2s electron wave। हम स्टैंडिंग वेव की बात कर रहे थे ना, तो एक वेव से दूसरे वेव प्रोफाइल में जो चेंज हो रहा है 1s से 2s में, दोनों में स्फेरिकल ही सिमिट्री है, so there is no change in the symmetry of the system, there is no, and therefore there is no dipole is developed। बट इन दिस केस, सेकेंड केस में जो पिक्चर है वो क्या है कि 1s से 2p, when a 1s wave, 1s is a electron, three-dimensional electron wave, and that 1s electron wave transforms into a 2p kind of thing। So electron distribution, you can see the electron density profile is changing and it is getting asymmetric। So यहाँ पे पहले initially electrons were here, now they are not here। येलो कलर वाले में तो यहाँ पे है ही नहीं इलेक्ट्रॉन, यहाँ पे इलेक्ट्रॉन था, अब यहाँ पे है ही नहीं, है ना। So you are having a change in the electron distribution profile, okay, you are getting an asymmetry in the electron distribution profile which was initially not there। So the second one is able to develop a dipole whenever there is asymmetric charge distribution, a dipole is developed। Whenever there is asymmetric distribution of charge, a dipole is developed, and this dipole is able to, this dipole we call it as transition dipole in this particular case। whenever you have, so this is what we say a transition dipole, जो ऊपर हमने टॉप में लिखा है, ये ट्रांजिशन डाइपोल यहाँ पे डेवलप हो रहा है। so 1s 2s both same spherical symmetry, like so there is no dipole is developed, but you can see here when 1s transforms into 2p, there is so when you are talking about 1s to 2p, there is 1s to 2p, there is asymmetric charge distribution, overall the charge migrates asymmetrically, okay, there is migration of charges, the electron density is now shifting from initially the blue color one जो यहाँ पे था अब नहीं है वहाँ पे, और इधर येलो वाले रीजन में इस तरह से आ गया है। So now you have asymmetric charge distribution when you are looking the transformation from 1s to 2p। So due to the asymmetric charge distribution, so you have different symmetry, asymmetric migration of charges, very carefully look at the points, migration of charge, a dipole is developed, right? And this dipole is what you call a transition dipole। और इसका जरूरत क्यों है? It is important because this transition dipole is important because this is a dipole which will interact with the electric field of the oscillating electric field vector in the light। Light, when you are viewing light as a wave, the light has oscillating electric field vectors, this transition dipole interacts with oscillating electric field in light wave. लाइट में जो ऑसिलेटिंग इलेक्ट्रिक फील्ड है उसके साथ इंटरेक्शन होगा और तब एनर्जी एब्जॉर्ब होगा। ठीक है, ये पहले वाले केस में व्हेन वी आर विजुअलाइजिंग 1s to 2s ट्रांसफॉर्मेशन, when a 1s electron wave transform into 2s, there is no such asymmetric migration of charges. There is same symmetry of the two orbitals. The electron distribution profile remains same. There is no dipole developed, and as there is no dipole developed, there is no interaction with the electric field vector in the light wave, and so there is no absorption. सिंपल। अभी तक हमने डेल एल की बात भी नहीं की और हम सही आंसर पे पहुंच गए। देखा, वो बाद में आता है, ये पहले आता है। पहला कंसिडरेशन हमारा है डाइपोल का डेवलप होना। ठीक है, ट्रांजिशन डाइपोल डेवलप होना चाहिए। अगर डाइपोल मोमेंट नहीं आ रहा है देन देयर विल बी नो इंटरेक्शन विद द लाइट वेव, और इंटरेक्शन नहीं होगा तो ट्रांजिशन नहीं होगा, नो मैटर हाउ मच एनर्जी आप मैच कर दें। ठीक है, सो दिस इज इंपॉर्टेंट, राइट। व्हेन 1s इलेक्ट्रॉन बिकम्स अ 2s इलेक्ट्रॉन, यही मैं बार बार बोल रहा हूँ कि अब आप इस तरह से सोचना शुरू कीजिए कि जब भी मैं कहूँ इलेक्ट्रॉनिक ट्रांजिशन हो रही है, मतलब एक इलेक्ट्रॉन जो कि वेव है, थ्री डायमेंशनल वेव है, वो दूसरे टाइप के थ्री डायमेंशनल इलेक्ट्रॉन वेव में ट्रांसफॉर्म हो रहा है। ओके, एंड ड्यूरिंग दिस ट्रांसफॉर्मेशन there must be a dipole that should develop, which is called transition dipole. And if that dipole is developed due to that, then it will be able to interact with the electric field vector of the light wave, and absorption will happen. Okay, so that's what we say. This is very fundamental to understanding of any electronic spectroscopic transition, whether it's happening in an atom, whether it's happening in a molecule, or and currently what we are discussing in a metallic and complex. Okay, किसी भी केस में ये बहुत ही जरूरी है। फर्स्ट प्रायोरिटी, फर्स्ट थिंग, फर्स्ट condition is that a transition dipole should be developed, and for that there must be asymmetry during the change in the wave profile of the electron. Okay, इलेक्ट्रॉन का वेव प्रोफाइल चेंज होगा। ओके, सो जैसा कि यहाँ पे देख रहे हैं, सो यू हैव asymmetric migration. So these arrow that you see, these are showing the transformation of electron density, asymmetric migration of charges. So when a 1s electron becomes a 2s electron, there is a spherical migration of charge and no dipole is developed associated with that. So it is, no dipole is developed, there is no interaction with the electric field of the light wave, so this will not happen, or we say that it is electric dipole forbidden, और इसी को हम कहते हैं। तो एक ट्रेंड जो हमें नजर आता है उसी को हम एक स्टेटमेंट देते हैं, वो कहते हैं कि रूल बन गया। ठीक है, फंडामेंटली समझिए, एवरी रूल हैज एन एक्सप्लेनेशन, एवरी जनरल ट्रेंड, the observation of a general trend is given in a form of statement, we call it rule. But basically all of them has a lot of discussion and logical thinking gone behind it. Okay, so this is how we can explain a transition in a hydrogen atom, and that's the thing that so in contrast, when we have 1s electron becoming a 2p electron, there is a dipole which is developed due to the asymmetric migration of charges, and now because a dipole is developed, this dipole will interact with your electric field in the present in the light wave, and the transition will happen. Okay, so this is how we explain the first rule that comes out to be. So there must, selection rules are just based on these things, that you must have net, so this dipole moment must not be zero, that we are talking about transition dipole, so which is applicable to both atomic as well as molecular spectra. Okay, uh, so usually, so change in quantum numbers or something that we talk about. uh, so the first things, so that was the first thing that we learned. And the second thing is that, so क्या क्या होता है, पहले आपका energy of the light must match the energy gap, one. Two, during the transition there must be sufficient asymmetric distribution of charge. So during the transition, asymmetric migration of charges must be there, just like S to P. So when we say one is in case of mm, so it is the interaction of light with matter, interaction of light with the molecule, and that will happen when there is a dipole which developed during the transition. During the electronic transition, there must be a dipole developed. So when 1s to 2s transition we are visualizing, there is no change in the there is no dipole that is developed. But when we are talking about 1s to 2p, there is a net dipole which is developed due to asymmetric migration of charges, and that is able to, so because of that, interaction happens with the electric field, and now you can have, so this is mu. So Fi that we have transition dipole, we visualize it, is nothing but integral we verify, talk about it in terms of transition dipole, which is integral of psi final mu dipole moment operator into, so mathematically this is how we explain this. Okay, so this psi f and psi I, the other final wave function, initial wave function. Okay, so when we are talking about final one as 2p, 1s in case of this, then this is happening because net dipole is developed. Okay, and when it is 1s to 2s, there is no dipole developed, so this mu Fi must be, so it must be a finite, must be must have a finite value. Okay, must not be equal to 0, that's what has been stated over here. Okay, so this is the thing that goes into making of this explanation of these rules. And stronger is the dipole developed, more better will be the interaction. अब transition dipole तो develop हो गया, transition dipole का magnitude जितना ज़्यादा होगा उतना अच्छा interaction होगा और उतना ही ज़्यादा light absorb होगा. So ये चीज़ देखने को मिलती है. So once you understand these things, so the second, so two parts, energy match del E must be, so we talked about one thing, del E, energy gap of which was E2 minus E1 must be equal to h mu. Okay, so energy gap of the quantized energy levels, this was the, so this is what we first, so that energy gap and this energy of the light must be matched. Light wave. Second, we just learned that a transition dipole mu Fi, second condition, it should not be equal to 0. And without going into mathematics, I told you how we have understood the point, that the shape, the profile, the overall, the distribution profile must undergo a change. There must be asymmetric migration of charges such that a transition dipole is developed. So this is what we know as transition dipole. Okay, dipole moment. Okay, this must be there. And there's also one more thing that you have not yet considered, conservation of the angular momentum. अभी तक एक और चीज मिसिंग है जो अभी हमने कंसिडर नहीं किया है, और ये सब सारी चीजें हमारे कंजर्वेशन ऑफ एंगुलर मोमेंटम। अब आप एक और चीज देखेंगे, सो द लाइट इज a photon angular momentum of what, basically of the whole system, but practically it turns out to be that of photon is, क्योंकि जब फोटोन एब्जॉर्ब हो जाएगा उसका एग्जिस्टेंस खत्म हो गया, उस उसका जो एनर्जी था वो तो आपने यूज कर लिया E1 से E2 ट्रांजिशन में, सो ट्रांसफॉर्मेशन, but you know photon also has angular momentum. Do you know that a photon also has angular momentum? और वो you should be able to account for that angular momentum. Okay, and to account for that angular momentum, now you see when you have a transition, um, so there is one thing that मैं आपको बस बताना चाह रहा था कि ये क्यों इम्पोर्टेंट, ज़्यादा मैथमेटिक्स में नहीं जाऊंगा, लेकिन हाँ आपको जस्ट so when we try to conserve the angular momentum, आपको so then there is third point that comes in, which we also call as specific selection rule. there are दो चीजें selection rules में, दो चीजें होती हैं, एक gross selection rule. Gross selection rule is this development of this is your gross selection rule. A transition dipole must be developed, and then you have to be specific about the transitions. You must be able to conserve the angular momentum when a photon is absorbed. And what you should know here, from the fundamental point, a minute, I will just consider a few points. If I tell you something interesting here, when you talk about particles, there are two types in this entire world. There are two types of particles. All the fundamental particles have spin. Spin is as fundamental as mass. ठीक है, इलेक्ट्रॉन हैज मास, इट ऑल्सो हैज स्पिन, और वो स्पिन उसके साथ हमेशा रहती है. एक फ्री एटम इलेक्ट्रॉन में there is no it may not have this thing, what you say, it may not be part of an atom. It may not have orbital angular momentum, but it does have spin angular momentum. एक फ्री जो isolated इलेक्ट्रॉन होगा sitting at rest in vacuum in space, तो उसके पास spin is a very fundamental property, intrinsic property of all elementary particles. Spin is an element. Okay, and how do we, the classification scheme that I had shown you there, you understand this is very important to understand the transitions and why the selection rules have come in. बहुत important है, बहुत सारी बुक्स में नहीं बताई जाती हैं, बहुत सारी क्लासेस में नहीं बताई जाती, लेकिन कितना important है इसको आप 2 मिनट समय देंगे तो समझ जाएंगे. ठीक है, सो बेसिकली मैंने आपको बताया था कि स्पिन क्वांटम नंबर s होता है, जैसे इलेक्ट्रॉन का जब हम डिस्कस करते हैं, have I told you this, that just like so electrons, so when you talk about electron, we have considered it has angular momentum, and this angular momentum can come from the orbital motion, or it can also come from the spin that we have been talking about. So angular momentum has so the angular momentum magnitude of it will have magnitude of angular momentum, एक मिनट इसको इधर कर दें. So you can talk about the magnitude of angular momentum, which is given by under root s. This is a small s, sorry. So magnitude of angular momentum is given by s into s plus, sorry s लिख रहा हूँ यहाँ पे. ऑर्बिटल मोशन के लिए l जो क्वांटम नंबर है l into l plus 1 under root h cross. Similarly, the magnitude of angular momentum, so due to the spin also you have angular momentum, so magnitude will be given by spin quantum number s, spin quantum number, which is for an electron it is fixed. So any particle spin quantum number has fixed value l, you know, l is variable 0 1 2 3. This is variable but this is fixed. So this is giving you the magnitude. Again the magnitude will be given by ये समझ रहे हैं, spin, and then z component of the same of angular momentum, this is given by mlh cross. mlh cross is your thing. So इसी एंगुलर मोमेंटम का z कंपोनेंट बताने के लिए mlh cross है, जो which can vary as ml can vary plus l 0 to minus l. In a similar way, it will also have, spin will also have two components. This will be the magnitude, and this one msh cross, where this will be give you the z component of the angular momentum. अब जब बात हम कर रहे हैं in a similar way, so this is where ms can have values of plus half or minus half, right? So this is the half integral spin. We say that electron is a particle which has half integral spin. There are many particles, even protons have half integral spin. Neutron also have half integral spin. So s is equal to half. So this defines your magnitude of the spin quantum number, spin angular momentum. So spin angular momentum, and so it is a vector. It has both things, magnitude as well as direction. So the magnitude and this part, the direction part, is fixed by, so a vector has two components and this is fixed. So we have to account for the what we said, spin quantum number, spin angular momentum. तो हम जो बताते हैं स्पिन का, एक मिनट, लेट मी क्लीन अप द स्लाइड. Okay, so this now proton, so fermions, you have all these electrons, protons, neutrons, all of them have, in terms of spin, they behave like that. And there are also other particles which have s. So all of them, these particles have the small s, spin quantum number is half for all of them. Whereas bosons are particles which have half integral spin, bosons, and photon is an example. Photon has s is equal to 1 spin quantum number, so its angular momentum is s h cross, which is 1. Put the values. Okay, so under root 2 h cross is the angular momentum of photon, and this has to be conserved. जब लाइट मैटर इंटरेक्शन हो रहा है, इलेक्ट्रॉनिक ट्रांजिशन हो रहा है, उसमें ये भी कंजर्व होना चाहिए, राइट? अब आप देखिए, जब when the electron moves from, now this must be conserved. यही हमारी बात है कि must be conserved during transition. So whenever this is kind of spectroscopic transition is happening, this momentum has to be conserved. कहीं ना कहीं वो एडजस्ट हो जाना चाहिए, ठीक है? अब ये देखिए ये क्या हो रहा है जब हम what we are doing here, what we are, बहुत ध्यान से देखिएगा क्योंकि ये आपको बुक्स में नहीं मिलेगा, ओके? और हाँ, so now when we are thinking of 1s to 2, so 1s, n is equal to 1, ये 1s है, और n is equal to 2, so hydrogen atom, simple case, and we are thinking of whether we should, so 2s and 2p have same energy in hydrogen atom. This is the case of hydrogen atom, okay? So, and we were thinking about whether this should happen or whether this should happen. Electrons, where will the electron go? And we are saying, so if I now visualize this thing, when an electron goes from 1s to 2s, so transition from 1s to 2s, in that case, what is the change in the spin angle, change in the angular momentum? Angular momentum is what? When it goes from L is 0, here also you have L is 0, so change in angular momentum is 0. But when you're thinking of 1s going to a 2p orbital, 1 is to 2p, then what is L? L is 0 here, L is 1. In that case, what is change in angular momentum? The change in angular momentum is given by del L. So delta L here is 1, okay? Delta L in this case is 1, and the change in angular momentum will be delta L which is root 2 h cross. अब आप देखिए, so this is same as, which is same as angular momentum of photon, which is equal to photon के angular momentum के बराबर है. So when an electron is making a transition from 1s to 2s orbital, the change in angular momentum is 0, and you are not able to account for you are not able to conserve the angular momentum of photon. But when you are moving from 1s to 2p, जब आप 1s से 2p में जा रहे हैं, then there is, you are able to, the change in angular momentum is exactly the same as the angular momentum of photon. So you are able to conserve you are able to conserve the angular momentum of photon. So conservation of angular momentum is followed 100%, and that's why del L plus 1 in this particular case, or minus 1 in other case if the transition is reverse, or in so this kind of thing is allowed. We say that this is allowed because one photon has the change of one photon angular momentum must be there in the electron. The change in फोटॉन का एंगुलर मोमेंटम कहीं ना कहीं इलेक्ट्रॉन के एंगुलर मोमेंटम में एडजस्ट हो जाना चाहिए जब वो एक ऑर्बिटल से दूसरे ऑर्बिटल में जा रहा है, ट्रांजिशन कर रहा है. So that is happening when we see 1s transforming into 2p, but not when 1s goes to 2s, right? Similarly, it will also not happen when अगर आप 1s से 3d में करें. So if I am visualizing again the change 3s 3p 3d in case of hydrogen, then again you can think of this one. This will also not happen because delta L here will be 2, right? So delta L will be 2, which is much greater than the angular momentum of photon. So that will not happen, but 1s to 3p, this will happen. So this is how we think about the things we have to explain. So the transitions that we are seeing here, so these are the consideration जो transitions के लिए अभी हमने हाइड्रोजन एटम के लिए सोचा है. यही सारी सी चीजें कहीं ना कहीं एक कॉम्प्लेक्स के लिए भी अप्लाई करेगी. द बेसिक फंडामेंटल्स रिमेन सेम. ओके, you have to conserve the angular momentum of photon. Okay, you have to match the energy of the things, of the two quantized energy levels, right? And you must also, और उससे भी पहले आपको ट्रांजिशन डाइपोल डेवलप जरूर होना चाहिए. So there must be a transition dipole which must be developed, otherwise there will be no interaction with the electric field vector. So this is how we put it. So electrons and protons are fermions, photons are bosons, that we have s is equal to 1, because they, so electron protons we have told because the spin quantum number is 1, sorry, 1 by 2 here it is 1. And so the photons, so this is the very fundamental nature, and that what I'm not going into the details of the particle physics here, but it is that what we are considering here is that we must account for the this energy change. We must account for the conservation of spin of the photon. The photon has an intrinsic spin of 1, corresponding s is equal to 1, and change of angular momentum of electron must compensate for the angular momentum carried by the photon. Okay, and this is what we find, that when an electron moves from electron in a, say, in a d orbital can moves to a s orbital, we are not able to do that. The angular, we are having much more angular momentum change as compared to one photon. But if you are moving from d orbital to p orbital, that is possible. Okay, so s orbital cannot make a transition to s orbital. This is what we found in hydrogen atom, considering no change in electrons angular momentum. Okay, so because we are not going able to account for this thing, this is what we have already discussed, and we say, in other words, we say that these transitions are not allowed, they are forbidden. Okay, so in spectroscopic we say that this will not happen, this will not occur because of the basic nature. It is not following the sector principle of conservation of momentum. Okay, and so that set of things that determine these things, we call them as selection rules, statements that we make, generalize it. So delta L plus minus 1, it comes from there. Okay, uh, so this is the consideration, that change in the dipole moment. And then uh, okay, so now coming back to our complexes thing. So basic idea, I hope you have been getting what I am trying to tell you. अब आप वापस यहाँ पे हम आए. Okay, so coming back to the what we were initially thinking, so the similar considerations will apply here. Okay, and intensity of color. So the absorbance, the term that we have that is defined in all these cases is um, Beer's law is absorbance is log of I naught by I, which is given by epsilon L C. Epsilon is the molar extinction coefficient, molar absorption coefficient. So intensity of color is related to this. How strong is the absorption? Absorbance will be high at a given. So this is absorbance that is plotted in your spectrum. So at a particular wavelength. So any at a particular given wavelength, how much light is absorbed. So suppose you have 100 photons passing through the sample, how many of them is absorbed? They are matching the energy of the sample uh, transition, but how many of them are absorbed, that is given by this molar absorption coefficient. Okay, and if the molar extinction coefficient is high, a light more photons will be absorbed of a particular wavelength, and then we say that the color will appear intense because of that if epsilon is high. So molar extinction coefficient epsilon, it gives you intensity of color, is directly related to this stronger absorption. Okay, so we are going to account for all these things in this discussion. Okay, so so selection rules are a set of these statements which take into account the generation, that there is a dipole that must be generated, transition dipole must be there must be the photons angular momentum must be conserved, and so we put out as statements which satisfy these things under all set of conditions. So this was the Laporte selection rule that was given by German physicist Otto Laporte. So which says that only allowed transitions are those occurring with a change in parity, or there is there must be change in delta L. Okay, we have seen how it will happen. We have seen that to conserve the angular momentum of photon, delta L must change by plus minus 1 unit. We have also seen that no dipole will be generated if 1s goes to 2s. So for those reasons, there must be there must be a change in dipole moment when the photon is absorbed. Only then there will be interaction with the light electric field vector of the light wave, and the thing is photon is absorbed. So practically, in case of this, because they have center of symmetry, allowed transitions will be 1. So a dipole will be developed when something goes from G rate to 1G rate, center of symmetry, no center of symmetry, or vice versa. But if you are moving from an orbital of G to G or U to U, then there is no such dipole developed and transition cannot happen. Okay, so this is the G rate unGrade thing that we have described in while discussing the orbitals, molecular orbitals and atomic orbitals. So with respect to center of symmetry, so uh, so when we talk about this T2 G2 EG, this is forbidden because all of them have same symmetry constitution. G to G, G to G transition cannot allow. So why this cannot happen? Because there is no change in the dipole moment. There is no transition dipole that develops. So from a symmetric to asymmetric migration of charge is not happening here. And so this rule is going to affect your octahedral and square planar complexes which have center of symmetry. Okay, tetrahedral complexes do not have this center of symmetry, and therefore this rule does not apply. Okay, so we call intensity. So the intensity will depend on okay. Um, Intensity means molar absorption coefficient is low, then there's less absorption. Intensity is if the molar absorption coefficient is high, you have a very huge absorption is there, strong absorption, and the absorbance value will be high. It will appear dark in color. Something will appear dark in color. So these are the things. Uh, hmm. So when you look at this Laporte selection rules, it turns out to be all DD transitions as in octahedral complexes are symmetry forbidden. And with this S to P in Laporte allowed S to P, P to D, D to F allowed transition because del L plus minus 1. And now del L plus minus 1 is not the reason. The reason is the conservation of angular momentum, and you are trying to account for the angular momentum of photon, right? Reason is कभी ये मत कहिए reason is delta L plus minus 1. ठीक है, never say that. Say you are when you're trying to conserve the angular momentum of photon and you are point blank, you are on the spot. Okay, so whether when you are looking for S to D transition, P to F transition, del L plus minus 2, not possible, del L 0, this is not possible because here you are able to we are able to conserve the angular momentum of photon फोटोन का एंगुलर मोमेंटम आप कंजर्व कर पा रहे हैं, राइट. Spin selection rules tells you this rule states that transition that involve a change in spin multiplicity are forbidden. So this is again related to the conservation of angular momentum. Electrons angular momentum must be conserved. uh, Spin angular momentum must be conserved, and that's why there should not be a change in the spin value, spin quantum number. Okay, ms. Okay, so this kind of transition is okay, but here this electron which goes up in the in the excited state, when the spin has to be inverted, this is forbidden. So in case of d5 high spin complexes, this is the thing that you will encounter. If you're trying to excite this electron, energy is given and it must change its spin. So if it goes to the EG level, it must change its spin because all the two are already in having plus half spin. So because of that, again the conservation of spin angular momentum is not happening for the electron, and this will not occur. So these are forbidden transitions in a pure setting. Okay, so we have already consider these things: Laporte forbidden and spin. So usually we talk of two things: Laporte forbidden transitions or spin forbidden transitions. That is, in one case del L plus minus 1, or here the spin change. There should not be any change in the spin of this electron. The multiplicity should not change. Delta S must be kept to 0. So that's what we find when you dissolve manganese sulfate Mn2 plus. This is colorless because the transitions are forbidden because of the by the first selection rule. By the second consideration, spin of electron, so in because of the two reasons, these are forbidden transition. But when you go for permanganate and chromate ions, they are intensely colored, even though they have no electrons in the d orbitals. So d0 system, but still they have color. So these are charge transfer. We will discuss this later. And usually you will find that tetrahedral complexes, because they do not have center of symmetry. There is no center of symmetry. This particular rule G to U does not apply, and so uh, they have all tetrahedral complexes will have very strong colors. Extinction coefficient, that means extinction coefficient will be large. Extinction coefficient will be large, and that's what we are seeing here, epsilon max in 3D complexes, where it is Laporte forbidden, spin forbidden. The absorption happens because of breakdown of certain symmetries, considerations, and rules, but it will be very very weak, 10 to the power minus 3 to minus 1. So absorbance value will be very small, very low. Spin allowed but Laporte forbidden. They will be, so one of the rules has been is allowed is followed, but the other is not being followed, so slight higher than the previous case. But when you have spin allowed and Laporte allowed, you have huge increase in the epsilon value. So these are related to the intensities. Intensity is correlated with the extinction coefficient, which increases as the as you open as the system is following the rules which we have set for, considering the conservation of momentum and conservation. So electrons angular momentum, spin angular momentum, and the photons angular momentum. So when we are considering the last one is the charge transfer bands, as in permanganate, they appear very very high, large. They are intensely colored because none of these rules apply, which is we were doing for within one atom. So एक ही atom में जो transitions के लिए था वो इस तरह का था, within one atom, or here we were talking about transfer of electron from one atom to the other. ठीक है, थोड़ी देर के लिए जो इलेक्ट्रॉन ट्रांसफर होता है. So this is the difference, and in that case all the first three rules do not apply, and it is still I will do that. So there are certain relaxations. So why do we see forbidden transitions at all? ये क्यों होता है? इसको थोड़ा सा हम लोग डिस्कस कर लेंगे. आई थिंक इवनिंग में करते हैं. आप लोग तब तक थोड़ा. So I think I have already taken longer than 1 hour. So I'll stop here. So we'll discuss from here, why do we see forbidden transitions do occur, but why do they occur? We'll discuss this in the next class.